you all for joining this webinar series. And so this is, as you can see, this is the area that I'm planning to cover in this webinar. First, I will do some sort of an introduction into transport network and just give you an idea. What is the transport network? Something which most of you might not be very familiar with. And then I will do some sort of an overview on the transport network architecture, how existing transport networks look like, and what are the components, and what are the domains, and all that. And then I will cover design considerations and aspects, and what are the areas that you need to look at to when you are evolving a transport network, when you are changing a transport network to cater fifth generation network requirements. And then I will go through basics of 5G and 5G system requirements. And then I will do sort of an network evolution analysis on what are the areas that you need to focus when you are evolving a network. And then I will go through 5G fronthaul, synchronization, software-defined networking, segment routing, EVPN, open networking, optical transport, and all those areas I have listed below. So just to give you an introduction, so the first question that somebody would ask when it comes to transport network is, what is transport network? Okay, so if you take a typical telco mobile operator architecture, there are mainly three components to it. One side, you find radio access network, something which most of you are familiar with, something that you usually, usually if you have a mobile device, then the first thing that you would connect to would be the radio access network through the user interface, AI interface. And then you have core network. Then there are a lot of cell sites. If you take a typical telco operator, in Sri Lanka, there are around, let's say, 5,000 sites, cellular sites. So all those traffic generated from those cellular towers or cellular sites has to be taken towards the core network infrastructure. Usually, a telco might have 2 to 3 or more than that. Core sites to cater those. Terminate those services. So transport network is something in between the radio access network and also the core network. But the most important thing that you have to understand when it comes to transport network is, if you take radio access network and at the same time if you take core network, radio and core network are governed by standard specified by 3GPP, third generation partnership project. It's a consortium. So transport network, if you take transport network evolution is not governed by those standards in 3GPP. But there are a lot of, predominantly covered by IETF, IEEE, ITUT, things like that. So the evolution is not quite aligned with 3GPP. So there are a lot of things that you need to understand when you are upgrading transport network to cater fifth generation network requirements. And so those are the constituents of the transport network. So typically transport network consists of IP MPLS routers, switches, then fiber infrastructure, microwave links, then DWDM and OTN equipment, GPON systems. So we will go through them when we move through the presentation. Okay, so this is sort of a slide that I wanted to present because I just wanted to give you some sort of an abstract overview of how a transport network would look like from two different aspects, two different dimensions. One is you have to look at transport network from a domain perspective. So just to understand, so domain means where those equipment lie in the transport network. Let's say if it is close to the radio access network, then radio cell towers, then that domain we can call it a fronthaul network. If it is a 5G case, or maybe fixed access. Then in the middle, from cellular tower, the cellular tower towards the back end, the back end of the telco network. Then we can have metro access, then metro aggregation, the IP MPLS core, and ISP and international networks also may have components of transport network. So those are the certain domains that you have to identify when you are analyzing a transport network. At the same time, so in a transport network that you would be dealing with IP and Ethernet and also TDM technologies, or maybe DWDM and OTN technology. So you have to understand things from a layers perspective. Okay, which layer those protocols belong to, and how those things are evolving and all that stuff. So typically, a transport network would have optical layer, that means layer 0, and then OTN layer. Then on top of that, then IP and Ethernet layer. So it depends on the operator. From operator to operator, the layers of a transport network could differ. So that's something that you have to keep in mind. So this is sort of a typical architecture of a uh, telco transport network. So it will consist of metro access rings, as I mentioned previously, metro aggregation rings. Then it could be a ring-like architecture. It could be mesh. So it depends on the operator. Then IP MPLS core, and then so here at the left side you can see there could be micro infrastructure as well. Like this is, I mean, like if you take micro network evolution, now it's in a phase of getting phased out gradually because of fiber penetration and all that stuff. But if there is some sort of rural requirement where you need to cater backhaul requirement, then you can have micro network as well. But this is something that is getting phased out over the last couple of years. And then at the same time, there could be passive optical network infrastructure, predominantly based on GPON, gigabit passive optical networks. So there could be optical line terminals and then optical network units. Well, well, I mean, if you have FTTX infrastructure, so those ONUs and ONTs will be the last mile. So other thing is here on top of, I mean, like over here, those metro access, metro aggregation, and IPMP, let's go IP Ethernet infrastructure. So below that, there could be a DWDM and OTN layer to carry those client signals. I mean, like if you have to, I mean, like for example, if you are an operator coming from, I mean, like a legacy operator has been there for some very long time, then it is, it's possible that you have DWDM and OTN layer because there are certain things that you may need to do to like carry multiple services, TDM services, multiple services on a DWDM and OTN network. So it's possible sometimes some operators may not have a DWDM and DWDM and OTN network. And below that, it could be fiber infrastructure. And on on top of all those, there could be different EMSs and NMS systems from different vendors because some operators don't want to be vendor locked in, so they have different network infrastructure and equipment from different vendors. So because of that, then there could be different EMS and NMS systems. On top of that, then there could be northbound APIs exposed into OSS and BSS layers. So this is how a typical transport network would look like. And I mean, like in 4G, I mean, like for example, catering 4G requirements. So before going deep into the technologies related to transport or transmission network, I have listed down, I mean, like I have built a sort of a hierarchy. What are the aspects that you have to look at when you're designing a transport network? So if you're designing a transport network, then you have to look at how you, I mean, like how scalable your infrastructure is, how, I mean, like to bring scalability into the network. So that means you should be able to do your capacity upgrades and network upgrades in a scalable manner without having to phase out entire infrastructure to introduce some sort of a new feature. And the other thing is you have to look at how resilient your transport network is. I mean, like if there is some sort of a node failure, or if there's some sort of fiber failure, if there's some sort of a link failure or micro link failure, then the network infrastructure has to be resilient. And the other thing is you have to look at how you can bring performance into the network, how you can cater latency requirements, how you can cater certain service level objectives, and then security aspect of it, and also the how you can reduce the cost in upgrading or bringing in new technologies. Then you have to look at how simple that you can make, because I mean, if you look at nowadays transport networks, most of them are very complex because there are a lot of protocol complexities there. So there has to be a way to simplify the transport network from a protocol perspective as well. And the other thing is interoperability is also another aspect that you have to look at, because most of the operators don't deploy transport networks with single vendors. The main reason is to avoid vendor lock-in, and so it's possible that they have multiple vendors, and multiple vendors may not be in agreement to support certain technologies. Like interoperability would be a big issue. So that's another aspect that you have to look at when you're phasing out or phasing in new technologies. Then that's another aspect. And the other thing is how manageable your infrastructure is. And uh, so we will go through all those design principles in detail in the upcoming slides. And at the same time, you need to look at different transport network aspects. I mean, different, because if you take a transport network, there are a lot of protocols, different specifications that you need to follow, and then you have to look at the topologies, what kind of topology that you're going to adopt, and then how you're going to upgrade the capacities. And let's say if you're at 400 gigs capacity, then how are you going to upgrade it to 800 gigs and all that stuff? What are the candidate technologies? So you need to understand that. And the other thing is what kind of transport technologies that you're going to use. So we will go through this in detail, and also vendor ecosystem. So this is sort of a brainstorming slide that I have created, just to give you an idea what kind of aspects that we have to look at if you're designing a transport network of facing a new technologies. On one side, you have to look at what kind of topology that you're going to adopt. Let's say if you have a network based on ring-like architecture, whether you're going to go into a mesh-like architecture, whether you're going to adopt a claw architecture, which is quite prevalent in data centers. So this is some aspect that you have to look at if you're designing a transport network into the next generation. So we will go through some of those areas in the upcoming slide. And the other thing is the capacities. So currently we are at 400 gigs. I mean, like as a world, and 400 gig deployments are quite prevalent nowadays. And then 800 gig trials are already going on with new transceivers with QSFP-DD and OSFP. So those are the areas that you have to look at. I mean, like if you are purchasing, or if you're taking in, I mean, like a new vendor, and you have to look at what kind of interfaces that they can support, different form factors, whether you can bring in new client signals into your network interfaces and all that stuff. So that's another aspect that you have to look at. Then transport technology, it could be IP Ethernet. So let's say the next iteration, in which direction that you want to go in, like whether you want to adopt segment routing V6. So those are, I mean, this is another aspect that you have to look at. And apart from that, then there are other aspects that you have to look at. That is, when you're bringing in new hardware from different vendors, then you have to look at how their ASICs and NPUs are designed. Because it is very important if you're rolling out new features in your service architecture. Then system specifications, whether, I mean, like clock synchronization and different IPS certifications. So if they meet those specifications. And apart from that, then you have to look at, I mean, like the network equipment, network operating systems, and how those network operating systems are designed, and the specifications, and whether they are scalable, whether they can be deployed on different hardware infrastructure, things like that. So on the right side, you can also see sort of a list of protocols. I mean, like this is not everything, but list of protocols that you may often see in a transport network. White highlighted ones are the ones I think in the upcoming years we will see a big change. I mean, like a big extension. I mean, like if you take for an example, BGP and multi-protocol BGP is going to be there for a very long time in the future with segment routing and segment routing V6 and ISIS. It's a routing protocol. So path computation element protocol and SRMPLS, SRv6, those are new protocols that would come into the picture when we migrate to transport network in the upcoming years. So at the same time, you have to look at different synchronization standards. And so if you are carrying synchronization information from grandmaster, clock grandmaster towards the edge of the network, then there are a lot of new standards that already have come up. And so those are the areas that you have to look at. So previously I did some sort of an overview, sort of a brainstorming slide which explains what are the aspects that we have to look at. So before going into uh, different aspects of transport network, for 5G transport network, I will just try to give you an idea of some sort of a primer on 5G. So I mean, most of you might have heard of 5G or already have some sort of familiarity with fifth generation networks of 5G, and what kind of capabilities 5G has and all that stuff. But if you, I mean, like to make it simple, 5G has three main pillars. One is enhanced mobile broadband, and the other one is ultra reliable low latency communication, and the other one is massive mesh type communication. So to cater those requirements, then from a radio network perspective side and also from core network perspective, then you need to have certain uh, capabilities in the transport network itself. So if you are moving from 4G to 5G, then the cell peak throughput will increase up to like 10 gigs of or 10 gigs of more than 10 gigs 10 gigabits per seconds, and then you will need to cater latencies below or almost equal to 1 milliseconds, and you will need to work then you may need to connect multiple millions of devices to a cellular tower. So there are a lot of requirements from 5G perspective. So whether you can cater those things in a transport network or not will matter based on how you design the transport network and how you introduce those new technologies to the transport network. So also you have to think about the timing accuracies and all those things. So uh, on the right side, you can see if you analyze 5G, then we are currently at release 17. So 5G started with release 15, 16, now 17. Now after 18 and 19 and 20, so we can call it 5G advanced, 5.5G. So there are a lot of new improvements or innovations coming in with 5G, like non-terrestrial networks, and also how you would broadcast and multicast using 5G radio. So there are a lot of new technologies coming in, and you got to be cognizant of what are these new requirements coming in, and how you can cater those with with the 5G transport network. So if you look at the numbers globally, more than 45 countries have already deployed 5G standalone already, and more than 80 operators. I mean, this is some sort of a report that I have taken from uh, GSMA. So more than 80 operators by 2022 has already deployed 5G standalone. Okay. So this is sort of an big overview of the areas that I'm planning to cover. So if you look at transport network, you have to look at how you would evolve IP, Ethernet, and or layer 2 and above protocol stacks. Then in that case, then you have to think about Flex OTN, Sigma routing, MPLS, Sigma routing V6. I will cover those areas in detail in the upcoming slides. And then how we would migrate your existing layer 2 and layer 3 services to EVPN. Then there's a new interesting area. Like most operators might need to focus on something called near package optics and co-packaged optics, something which is prevalent in date. Early deployments are already going on. Early trials are going on with near packaged optics, co-packaged optics. So the way we build or create hardware will drastically change with NPOs and CPOs. Then there's a lot of interest towards open networking. So we will cover those areas. And then we have to look at how we would evolve IP and optical layer, and whether we're going to keep DWDM OTN networks further. And there's a lot of traction towards IP over DWDM. And then we will go through open optical standards and also open optical evolution. And at the same time, we will do sort of an I will do some sort of explanation on 5G front hole and different 5G front hole options. And then and at the same time, I will do some sort of explanation on network management, orchestration, and also telemetry, and also software-defined networking. Okay, let's dive into 5G front hole and synchronization requirements. So at the left side, you can see this is how a typical cellular tower would look like. In the past, let's say if it's a 2G system, then at the top you can see this is those are antennas of a cellular cell tower. So we used to have some sort of a baseband cabinet, BTS cabinet at the bottom at the cell tower. So we used to draw RF cables. With 3G and also 4G, we changed this architecture of a typical cell site to have a radio unit, a new equipment called radio unit, and we kept that radio unit at the top of the cell tower. Then we will connect all those antennas to this radio unit. Then we will draw fiber cable, okay, towards the baseband unit at the bottom of the cellular tower. So we can call this as a sort of a front haul. This would be carrying radio samples in phase and quadrature radio samples towards the baseband unit through some sort of a fiber. So this there's a standard called CPRI, Common Public Radio Interface, and also there's another standard called OBSI. So CPRI used to be the predominant standard of carrying radio samples towards the baseband processing unit. So 5G with 5G, there's a huge change in this infrastructure, how you would arrange a cellular tower in 4G E not B or G not B, and in 5G G not B. So we made a split. I mean, like if you take a typical baseband unit, so baseband unit may consist of different LTE protocol stacks. So if you take LTE, and how a baseband unit would process different radio samples and do the communication with the core network and also with the user interface. There are a lot of protocols, especially for like specified in 3GPP. So there are protocols like radio resource management, RRC, PDCP, and RLC, MAC, PHY, and RF means radio. Then in previous generations, we used to have this RF functionality, radio processing functionality at the top of the tower, and we would carry those radio samples towards the baseband unit. But with 5G, there are a lot of split options introduced by 3GPP, from option 1 to option 8. And what we would do is we would split some of the functionality, low fi and RF functionality, and we will bring that functionality to the radio unit at the top of the cellular tower, and then we will bring we will do other processing, that means higher RLC to higher file layer at some sort of a centralized location. So we can connect multiple radio units to this distributed unit. So this is responsible. I mean, like at the bottom, you can see here there's a radio unit, then there's some sort of a distributed unit we can call. So those DUs are implemented on FPGAs or ASICs, and the processing will happen in specialized hardware. Or sometimes if it is a uh, sometimes sorry, sometimes I mean, like here you can see an RU radio unit where you would do lower 5 processing, and then you will carry those information towards the DU. So in 5G, there's a new standard, couple of new technology standards introduced. One is called eCPRI, and also another called Radio over Ethernet to carry those radio information over the front haul infrastructure. Then higher RLC and above layer processing will happen at the centralized unit. So we can call the link between a DU and CU a mid haul, and then RU and DU we can call it a front haul. So this is how typical front haul infrastructure would look like. So you might ask, so what's the applicability of a transport network in this kind of scenario? Sorry. So the what happens is, when you have this kind of infrastructure, then the amount of traffic requirement between RU and DU would be very high. I mean, like if you take a typical radio doing a higher configuration MIMO and doing carrier aggregation and working in different frequencies, then you will have very stringent, very high traffic requirement. So you need to cater that. So to do that, we need to introduce some sort of a transport network and in between the RU and DU. So this is sort of a representation of how RUs and DUs will look like. And modern way of doing this is to have DU and CU implemented on commercial off-the-shelf hardware. So this is also another representation based on how you would do this split, higher layer split and also lower layer split. You will get a different kind of functionality. Like let's say if you bring split down, let's say if you do more radio processing at the radio site itself, then you will get more RF gains. And if you bring a protocol split to the upper layers, then you will gain more reduce capacity requirements for the transport network. So this table, you can see some of those latency requirements to cater this transport network between DUs and CUs. Usually it should be between 25 milliseconds. 5 milliseconds to 25 milliseconds. And if you take a mid haul, then for the front haul between radio units and DU distributed unit, the latency requirement should be, requirement should be in sub 100 microseconds. So depending on the vendor and also depending on the implementation, those numbers could differ. Uh, so those are few options. I mean, let's say if you are building a transport network, then there are multiple options that you can look at. And one option is to use passive WDM technologies, and that means multiplexers and passive equipment which does not require power. Then you can look at the options like active WDM, where you can, let's say, you can do OTN, you can do uh, transponder functionality, you can have transponder functionalities. Then you can build your front haul network based on GPON and GPON2, but there are difficulties in, for example, if you are trying to distribute time and time synchronization information, then that would be not a good option to go for. Then other option is IP Ethernet infrastructure to build a front haul. So this is the most promising option if you are building a front haul network, because you can have functionalities of operation and administration management, OM functions, and so many things. And at the same time, from a cost perspective, so this can be also cost effective compared to other transport network, I mean, like front haul options that you can consider. And also you can consider direct fiber if it is if it feels like a good option based on how you what kind of fiber infrastructure that you have in place. So this is sort of representation how you can build a IP Ethernet front haul network. And there are a lot of new technology specifications and vendor equipment already available to build front haul networks based on IP and Ethernet. At the same time, TWDM, GPON is also another option if you don't have very stringent time and synchronization requirements. And WDM control is a good option also. It depends on the cost and the fiber infrastructure that you have in place. Okay, when we talk about 5G front haul and also 5G transport network, then synchronization is also a very important topic that we need to talk about. I mean, what it means by synchronization is that you should be able to distribute accurate frequency and phase information. I mean, frequency and phase together, you can call it time information towards the edge of the network. So if you are doing, I mean, like in the previous generation, let's say 2G and also 3G and LTE FDD, frequency division duplexing, you did not have very stringent requirement on time. That means phase synchronization. But with 5G, I mean LTE advanced and also LTE TDD, and also with 5G, there's very stringent requirement to distribute timing information from the clock sources or maybe GNSS receivers uh, towards the edge of the network. Okay, so this is very important aspect. So, and if you, I mean, like this is sort of an introduction into time and synchronization. Just to, I mean, like before I dive into what are the requirements in 5G from synchronization perspective. So in synchronization, you can take phase and frequency. Then there are ways that you can distribute phase information. One is through PTP. It's a protocol defined by IEEE. So now the latest iteration of PTP is IEEE 2008. IEEE, I think in 2019 there's another new release, PTP 2.1, and then you can also use GNSS to distribute phase information. And also from frequency side, you can also use PTP, and also you can use SyncKey to distribute. I mean, SyncKey is not is a layer, physical layer technology. So you to distribute frequency. So there are a lot of ways that you can do time and frequency and phase distribution of a telco transport network. So there are a lot of telecom profiles defined, and so when it comes to 5G, then I mean, like compared to the previous generations, biggest issue that you might face is you're gonna need very accurate time synchronization between, I mean, time error budget between different cellular sites. That means if you are deploying transmission diversity, then you're gonna need plus or minus 32.5 nanosecond transmission diversity, and relative time accuracy should be at around 20 nanoseconds. And if you're doing carrier aggregation, then it will be around 100 nanoseconds. So time synchronization is very important. So if you are, let's say, if you're taking, I mean, like if you are choosing a certain vendor uh, to distribute more accurate time towards the edge of the network, and then you're going to need more accurate time. I mean, like equipment supporting higher classes of different, I mean, like specifications defined by ITUTs. I mean, G.8273.2 is a sort of a specification which defines what should be the uh, a time error budget of a network equipment when you pass timing information from node to node. So in 5G, it should be in class C and also class D. That means accuracy should be in 10 nanoseconds or something like that. So there are a lot of requirements. I think I don't have time to go through all those the technical stuff related to timing and synchronization, but I'm hoping to do some sort of a session later in a separate webinar about 5G time and synchronization. So we'll see. So another aspect uh, in in a transport network, I mean, like when you're designing transport network, is how you can introduce software-defined principles into a transport network. So before diving into software-defined aspects and how you can introduce software-defined networking into transport network, I will just give you some sort of an understanding what it means by software-defined networking. So if you look at the early ideas of software-defined networking, the idea was to have centralized control plane and to have a distributed data plane everywhere. So here in this diagram you can see it. So you will take the intelligence of each and every device, the control plane and also management plane, and you will put it at a central location, and then you will try to manage the equipment, I mean the flow tables from the central component. So this was the initial idea of software defined networking, to have a central software defined networking controller. But the issue with this kind of architecture especially in transport network is the southbound API I mean, like efficiency is a big concern. At the same time, you would not be dealing with the network with two or three or something like that, very small number of routers or switches, because you'll be dealing with hundreds of thousands of network equipment and distributed across large geographies or geographical areas. So you need to have some sort of a I mean, like southbound API information. I mean, like efficiency will actually will matter that kind of scenario, because uh, let's say if there's some sort of a node failure or a link failure, then you will have to update the network state, because network state is at the center, like at the SDN controller. So distributing or populating different TCAM tables, or maybe tables that you have on each and every device would be a cumbersome task, and the efficiency will not be there to cater those requirements. And so you'll be dealing with 100 gigs of traffic. So that some node failure will have a huge impact on a node, or link failure will have a huge impact on the network itself. So that's one of the reasons why I moved away from this kind of architecture to have central SDN controller and to distribute a data plane. So the best approach is to have some sort of a hybrid control plane. So we will go into the details when we move into the segment routing section. So the best option came in the, I mean, like if you take transport network hub, you can introduce software defined principles to transport network programmability, control, and automation, and all those things. Especially programmability and control, then software segment routing is the way to go. So we'll get into that. So this is sort of a mind map of software-defined networking. I mean, if somebody asks me the question, "What is software-defined networking?" It's not something that you can easily define, because there are a lot of ways that you can define software-defined networking, and there are a lot of traits. There are different visions. So it is not just a separation of control and data plane. So you got to think about overlay networking. There you got to think about automation and orchestration. Then hardware and software disaggregation also can be taken as a part of software-defined networking. So there are a lot of ways you can do that. And if you take a software-defined transport network, and nowadays, and I mean, like working transport network, I mean, I should say, how you would truly evolve a transport network into software-defined principles, then the best option is to go in the direction of segment routing MPLS and segment routing V6. And then you need to have orchestration and automation, and also disaggregation is a good option. And then you can think about other transport SDN aspects as well. Uh, so I will not go into this table, but because I will explain those things in the upcoming slides in detail. So this is sort of an end-to-end view of how you can bring software-defined principles into a network. I mean, to an end-to-end telco architecture. So there could be, let's say, if it's an IP Ethernet domain, then you can have some sort of a IP SDN controller. So in segment routing case, it could be a path computation element. And so you can have different equipment from multiple vendors. So like Cisco, Huawei, Nokia, Juniper, there are a lot of vendors can provide those types of controllers. Then in an optical domain as well, then if you have an optical domain, especially layer 0 and layer 1, then you can have an optical domain controller. And then in microwave domain, you can have a controller. And also with the recent advancement with the Telco Infra project, then even radio access network has options for controllers to run different XApps and RApps on top of different SDN controllers like ONOS. And then uh, in a data center environment, you can have the same principles. You can apply the same principles of software-defined networking to have some degree of centralization of control and to have programmability. So on top of that, on top of every controller, you can have some sort of a hierarchical controller. So this is sort of an abstract representation, but because this is not the way we would deploy a typical telco network architecture, it depends on the vendor implementations, and some vendors follow this, some vendors don't follow this and don't go in this path. So on top of this, you can have some sort of hierarchical controller from an abstract point of view, and on top of that, you can have some sort of a service orchestration or assurance system. So this is how it looks like. So down here, you can see who are the vendors who are playing. I mean, like working in each and every respective domains. So I will do some sort of a introduction into segment routing as well, because in the future, segment routing will play a huge role in every aspect of network. It does not. It is not limited to telco transport network. I mean, it would be there in the radio access network and even in mobile user plane, even at the core network, data center infrastructure. So it's very important to understand what kind of role segment routing will play and what is segment routing as well. So segment routing is not a. I mean, like it's not a complete. I mean, like it's a revolutionary approach towards certain problems that we had in telco IP/MPLS networks. So I will just give you an understanding how it works. I mean, usually in the MPLS world, we used to do multi-protocol label switching. That means we would do label swapping when you move from one node to another node and another node. Like that, when what we used to do was we do some sort of a label swapping. And to do that label swapping and also to distribute label information, we used to have protocols like LDP, and also to do traffic engineering, we used to have RSVPT. What is different with segment routing is that uh, we would put the stack of labels. I mean, for example, if you take a node A, node B, node C, and if you want to go from point A to point 1 to point 2 through this network, then you would specify uh, the nodes that you would have to traverse through at the beginning of, I mean, like when you start sending the packet towards the network. So, so the insertion of the packets or labels would happen at the edge of the network. So intelligence would be at the edge. So you'll put all those labels, what kind of segments that you will need to traverse and all that. So there are a lot of, I mean, in segment routing terminology, there are a lot of things. I mean, things like node seed, adjacency seed, prefix seeds, and there are a lot of seeds defined. That means you can take a certain segment, let's say link as a segment, a node as a segment, maybe a IPv4, IPv6 prefix as a segment. So this is how segment routing would work. And there are two flavors of segment routing. One is segment routing MPLS, and the other one is segment routing V6. And the main difference is data plane is based on MPLS in segment routing MPLS, and in IPv6 you'll be using IPv6 routing extension header information to carry those segment routing information. So this is sort of a representation how the packet would look like. So you will have the payload, and over here you have SR header with the IPv6 header, and also HMAC for security, and also SRH headers. That means list of nodes that you would traverse through, or maybe the program instruction. So in SRv6, you would use the IPv6 address itself to program the network. That means what kind of nodes that you need to traverse through and what kind of functions that you need to do. So there are a lot of end functions defined in SRv6. So like end.x and end.t. So there are a lot of motives behind those different functions defined in segment routing v6. Uh, so this is how a typical segment routing transport network would look like. You're gonna need, I mean, HR, I mean, hierarchical PC is not a standard yet defined, but it would be required if you have some sort of a multi-vendor network. So SRPC's main function is to do traffic engineering. Let's say you want to go from point A, point one to this point one to this point one. Then you're gonna need to. I mean, like let's say you want to take a certain specific path, then you can dynamically assign SR policies and which path you want to take and do that configuration there. So I will not go deep into the segment routing and segment routing PC because it will take some time, and hopefully we will do it in a separate session. And so segment routing, as I speak, is another, I mean, like a huge uh, innovation happened over the last couple of years since 2012, and many vendors have already adopted it and have contributed to those specifications. There are SR MPLS and SRv6 specifications that are defined in ITF RFCs. So the effort is already going on, and in the future we will be able to see segment routing everywhere, from radio to core data centers and everywhere. So that would be the de facto way of connecting things. And the other thing is, in telco architecture, we used to provide L2 VPN services, L3 VPN services, and those services are now migrating to EVPN. So there's a that means EVPN is also a BGP, another AFI value or SAF address family. So we will converge all those typical VPWS, VPLS services, point to multipoint VPLS services, VPLS and L3 VPN services, and also uh, L3 VPN or L2 VPNs that we used to have in data centers to EVPN. So it's a completely different address family that can carry multiple information, routing information, and routing information or MAC level information, so many information. And we can also migrate L3 VPN, existing L3 VPN in telco infrastructure to EVPN, but it's a choice based on the operators. So the entire architecture would look like is like this. So you're gonna have EVPN end-to-end telco architecture to carry different services, different mobile broadband services, ultra reliable low latency communication services, and then data plane would be segment routing MPLS or segment routing V6. So this is sort of a hierarchy. If you're designing a transport network based on segment routing, and then those are the aspects that you need to look at to understand. Sorry, to evolve a transport network. So you have to think about the traffic engineering aspect, how you can carry traffic on a specific path in the transport network. So there are options like segment routing, traffic engineering, and also flex algo. So SRT and flex algo are quite useful if you are doing network slicing in a 5G environment. So I believe FlexAlgo will be the de facto way of doing slicing in the upcoming years, and also SRT could be also useful to carry traffic in specific slices or in a specific path. And then if you're designing a transport network with segment routing, then you have to think about the IPv6 address plan and how you would allocate different IPv6 addresses, and also think about the because based on that a lot of things will depend, because if you because in segment routing itself there are a lot of challenges in compressing the segment routing v6 headers. So there are a lot of new standards from different vendors like Cisco, Huawei, and also Juniper. So there are competing standards, competing efforts to do segment routing v6 header compression. uh, so this is another area that telco must focus on if they're building a transport network. And the other thing is how we would interact with, I mean, if you are migrating existing transport network into segment routing MPLS, then there are a lot of aspects that you have to think about the interworking. So if you are migrating from MPLS to segment routing MPLS, then you can do that with the mapping server functionality. But if you are migrating from MPLS to segment routing V6, then there are difficulties in doing service stitching and all that stuff. So this is another aspect that you have to consider. Another thing is PC design or path computation element. So this would be the SDN controller. Uh, of a segment router network, then you need to think about how you would interoperate between different path computation elements. And another aspect is multicast services, how you would carry multicast services, whether you're going to phase out multicast services or you're going to migrate your existing PMSM or PMSSM infrastructure into uh, BA v6 or BA architecture. BA means bit index explicit replication. So how are you going to do that? And the other thing is how you're going to evolve the EVPN architecture. I mean, how you're going to evolve the existing L2, L3 services architecture into EVPN. And then you have to think about SRMPLS and SRv6 security, how you can achieve that. And also multi-vendor compression interworking. So those are pain points if you're designing a transport network and if you're migrating the existing MPLS network into segment routing MPLS or XRv6. So those are the areas that you should focus on and understand what kind of capabilities those different vendors have and what kind of roadmaps they have and whether you can do this migration and all that. So this is sort of a design, how a typical SR-MPLS or SRv6 design would look like. And I will not go very deep into the this kind of architecture, but there are two ways you can build an EVPN infrastructure. Whether you can have a flat architecture, that means end-to-end, cell site to cell site, flat EVPN architecture, or maybe you can have some sort of a hierarchical architecture where you have a common PE layer and you will terminate those EVPN services there, and then you will do the self stitching. So this is sort of an architecture how architecture would look like when you implement segment routing MPLS or uh, SRv6 and also EVPN. Okay, and this is an interesting area, network slicing. So uh, I will be doing another separate session on network slicing, separate webinar. But just for the sake of understanding, network slicing is the most popular use case in fifth generation networks. So what it means by network slicing is like you should be able to carry different kinds of traffic. Let's say enhanced mobile broadband traffic with a lot of bandwidth requirements and at the same time latency requirements, and maybe you need to have separate IoT slice separated from other uh, network slices. So to cater that, then there has to be certain things that should be fulfilled in a network from radio access network perspective, then transport network perspective, then to core network perspective. And so usually there are two ways of doing network slicing in a transport network. One is called hard slicing, another one is called soft slicing. So what it means by hard slicing is uh, you dedicate certain resources to like if you are carrying some traffic in the transport network, then you would dedicate resources to a slice. So there are technologies, candidate technologies like Flexi Ethernet to cater those. Like if you want to achieve hard slicing in a network, then you can use Flexi Ethernet. So I will go through Flexi Ethernet briefly in upcoming slides. Then you can also do soft slicing. Soft slicing is in soft slicing you don't have to dedicate resources in the transport network infrastructure. So you can do it with segment routing traffic engineering, and also you can do it with flexible algorithms. And another aspect in a transport network, for most operators, if you take most operators nowadays, they're considering the option of migrating, changing the existing infrastructure and to get rid of the vendor lock-in and things like that. So open networking is a good option to consider. Let's say if you have equipment from main incumbent vendors, then you should be able to take your network operating system separately and also hardware separately. So you get the economies of scale. Like if you can take different hardware from multiple vendors, multiple sources, and also if you can install your own operating system or your preferred operating system on the hardware, then that disaggregation can bring more cost benefit, also more control towards the operator. So there are a lot of options out there. Those are some of those vendors that I have listed down, some HCO, UFI and there are a lot of vendors out there that can provide uh, telco transport network equipment, especially cell site gateways, aggregation routers, and also P-layer routers, routing equipment. And so they can provide hardware, and you can install pretty much your own operating system or your preferred operating system on top of that. So to do that, there are a lot of dependencies as well. You have to think about what kind of ASICs or application-specific ICs or network processing units used in the hardware, and you have to think about sometimes I mean, like, you have to think about this software as well. Where, I mean, like, because there has to be some sort of a hardware abstraction layer on top of that, and so there are a lot of concerns that you need to things that you need to understand. At the same time, if you're replacing existing, let's say, cell site gateway with a disaggregated cell site gateway, that means disaggregated hardware and also with software, then you need to think about, let's say, whether it can support timing and synchronization requirements that you may have for 5G and all those things. So there are a lot of aspects that you need to consider if you are introducing open networking, but it is doable. And also, many operators have already deployed, many large tier one operators have already deployed more than 60 to 70% of their network based on open networking hardware. So this is another interesting area, a new trend among operators to try different hardware and software from different ecosystems. And for the optical domain as well, I mean, there is a organization called Telco Infra Project, started by Facebook or Meta. So they also have come up with different specifications to disaggregate optical equipment as well. Like, if you take an optical network, there are transponders that would convert gray optics into gray wavelengths into colored wavelengths, and then multiplexers, demultiplexers. So those optical line systems could also be disaggregated. That means you can take the operating system separately and hardware separately. So there are a lot of incumbent projects. Cassini is one of them, and also Phoenix is one of them. It's a muxponder and transponder equipment. So Cassini is a transponder, and so there are a lot of options out there for operators to consider if they are considering disaggregation in their transport networks. So, uh, so this is a optical. I in previous a couple of slides I talked about IP and Ethernet layers of the transport network. So optical layer is also something which is prevalent among many operators, and if that operator is coming from, has been there for, like, let's say, decades, then it's possible that operator may have this kind of infrastructure to have a separate OTN layer and DWDM layer, because they want to migrate from TDM infrastructure to IP and Ethernet infrastructure. So you'll have to carry multiple services in that kind of a domain. So you're gonna need to have OTN and also DWDM to do that, and that has been the prominent way of doing things. But nowadays there are other options, and IP over DWDM is another option. Instead of having different IP and optical layers and have multiple management planes to manage, uh, uh, and also to manage different layers and also different equipment. I mean, for example, if you take a traditional optical IP optical layer operator, they have, like, those are the things. I mean, you have to you need to have routing and switching equipment, then you need to have gray pluggables, you need to have fiber jumpers, gray, and also transponder muxponder cards and optical chassis, and then to have a maintain a separate optical infrastructure. So from cost perspective, this is not cost efficient, and also there's a lot of operational overhead. So IP over DWDM is another option to overcome this, and but there are pros and cons in both, and it doesn't necessarily mean having a multi-layered architecture is bad. But if you want to be more scalable, then this one would be the most efficient way of doing things. So you can, because if you want to increase the capacity of your transport network, then what you can do is you can introduce new wavelengths, and you can roll out a new wavelength and do the traffic steering in this kind of infrastructure. But in IP over DWDM, what you get is you simplify the infrastructure, you save the cost for power, you save the cost for space, and then you have less number of equipment to manage, and also the management plane complexity would be very less. So when you talk about optical domain innovations, another area is flexible Ethernet. I briefly mentioned that one in a couple of slides before. Flexible Ethernet is a standard, came back in 2016, and which is popular in mainly in China and Southeast Asian regions, not very popular in Europe and also North America. What Flex Ethernet brings into the table is something like this: that you can separate the TCP/IP stack MAC layer and also physical layer, and you will introduce new Flexi Ethernet shim. What you can do with this is that you can carry multiple MAC rates uh, and also match into different physical interfaces. So you can do channel bonding. You can do subrating, you can do channelization. That means you can match different MAC rates to different PHY interfaces. That means, let's say you have 300 gig traffic coming from, like MAC traffic, then you can distribute among, let's say, 300G interfaces. So that's the sort of flexibility that you get with Flexi Ethernet, and you can use Flexi Ethernet predominantly in if you're doing network hard slicing. So you will be dedicating resources. This is similar to a TDM technique. So that's why it is not very popular among some of those operators, and some may go in the direction of segment routing, TE, and flexible algorithms. But this is also another option that you can consider if you're migrating and if you want to introduce hard slicing in your transport network. Okay, when you're migrating a transport network, the optical transceivers is another interesting area and also a very important area that you need to consider, because you'll be spending a lot of money, a lot of, there'll be a lot of costs incurred on optical transceivers, and it's very important to understand what kind of innovations are going to be there in the upcoming years. So if you take a typical optical transceiver, then an optical transceiver mainly consists of digital signal processing units, DSPs, usually used for coherent transmission and to compensate different impairments, dispersions, and do dispersion compensations and all those things. Then you need to have transmitters and lasers, and there are different laser technologies like VXL, vertical cavity surface emitting, and also EML, absorption modulated lasers, and DML lasers. So those lasers have been there for some very long period of time, and typical infrastructure usually have this kind of lasers. And if you're doing coherent transmission, what it means by coherent transmission is, usually there are two ways of doing optical transmission. One is direct detect, and the other one is coherent. In coherent, you'd be carrying lambdas and signals with changes in the phase and also the amplitude. You'd not be only sending signals ones and zeros. You'd be carrying more information in a signal constellation, and you would be doing modulations like quadrature amplitude modulation. So we call this process a coherent transmission. So nowadays, most of those transceivers that we see doing coherent transmission use Mach Sender lasers. And the other thing is, you need to consider silicon photonics, and there's a huge innovations going on silicon photonics side. That is, what it means by silicon photonics is that we can put modulators, detectors, and those output couplers and lasers in a single ASIC die, and die, and also in a package. And the other area is NPU and CPU, near packaged optics and co-packaged optics, and so there are a lot of innovations going in optical transceiver domain. So uh, I want to explain this side, that this is CPU, co-packaged optics, what it means by co-packaged optics, because this is going to be the future of telecom equipment and also network equipment. That means you don't need to use transceivers. So in, let's say, next 5 to 6 years, you will not see transceivers. Predominantly in data center domain, uh, NPOs and CPOs are already in trial stages. That means you will be able to bring optical layer processing or SIF processing. Photonic ICs very close to the ASIC die in a network equipment. So you can reduce the the cost in terms of like the energy consumption, energy loss due to copper wiring that you have in a routing or switching equipment or main board. And so you can bring everything into a single package, or we can call it a co-packaged uh, co-packaged packaging, right? So this is another interesting area, and so in the future we will see less and less use of transceivers, and the requirement for transceivers will phase out. But predominantly we will be able to see this in data center space compared to transport network. But in next decade or something, we will be able to see uh, less and less photonics, less and less transceiver based hardware. Uh, so this is another this is sort of a representation of how the application specific evolution has happened over the last couple of years. So every 2 years, you see improvement in the ASIC processing. And so we are currently in the range of 800 gigs in terms of the transceivers, and in next by 2024 we'll be able to see 1.6T transceivers as well. And baud rates have also increased from 10 gigs to 25 gigs to 50 gigs, and now in the upcoming future we will see 200 gig baud rate capable photonic equipment. So if you're designing network equipment, then there are a lot of things that you have to understand: the ASIC that you select and silicon photonics that you select. So it's sort of a combination of cost, size, and power and requirements. So that's something that you have to keep in mind. And ASICs and photonic evolution is not happening uh, parallelly, and ASIC evolution is ahead of photonic evolution. So there has been sort of a lag of transceiver evolution for last couple of years, but with co-packaged optics and the CPOs and NPOs, we will see some huge improvements in the upcoming years. And there are a lot of efforts from different industry multi-source agreements. That means it's a sort of a consortium between or agreement between different vendors to introduce open optical solutions. That means, I mean, if you take like if you take two transceivers from two different vendors, then sometimes it would be difficult to integrate. I mean, they would not work very much if you connect to one vendor's router to another vendor's router using their own ZR optics. Most probably, it would not work. And so there are a lot of standards out there different with different vendor participation. So OpenZR Plus is one of them. So this is some area that telco should focus on, and if they are looking at or evaluating optics uh, for their transport network, and to look at the what kind of roadmap those vendors have and all that. And the other thing is application specific ICs and NPUs. So this is an interesting area. So, and if you look at modern telco equipment, most of them are from proprietary vendors. And the vendors make their own application specific ICs all by themselves, and they do the designing and then do the fabrication. But there's been a lot of attraction towards the merchant silicon over the last couple of years, and there has been a lot of new merchant silicon vendors like Broadcom and also Marvell. And so they make equipment, application specific ICs, general purpose ASICs that can be used in telco equipment. So that can give them cost benefit uh, compared to a proprietary silicon. So those ASICs come in different domains of the network. It could be in transport network access, transport network core, anywhere in the network, or maybe in the front door. So there's been a huge attraction towards merchant silicon. At the same time, there's been a lot of attraction towards programmable ASICs. In the past, if you design an ASIC, then bringing in programmability into that ASIC, I mean, like changing the match action tables that you have in a ASIC TCAM or maybe in ASIC pipelines would be a difficult thing. You cannot do that. And so since 2016, 2017 timeframe, there's been a lot of attraction towards programmable ASICs, and P4 another programming language came because of this aspect of ASIC programmability. So this is an interesting area. Then depending on your requirement, you have to understand what those ASICs are capable of and what those ASICs are not capable of. Because if you're making a sort of a purchasing decision to purchase an equipment from a certain vendor, then you have to look at what kind of capabilities those ASICs have, because depending on the ASIC, the feature rollout will depend. Because you would not be able to, let's say, for example, if you want to roll out segment routing V6, then some processing might not be able to, I mean, you'll not be able to do line rate SRv6 processing if you don't have the right kind of ASICs in your network. So that's a very important aspect that you have to look at if you're evaluating this aspect of the network. And I will go through another aspect in telco transport network, that is how you can bring service orchestration into telco network. So usually, if you take a telecom network, there are multiple domains, as I explained in the previous slides. One was front haul, and the other one was microwave, GPON. It could be GPON network, then IP transport network based on metro access, metro aggregation, IP/MPLS core. Then you can have some optical infrastructure and data center fabric. So what you would do with network orchestration is, like network orchestration means automation of automation. That means you would be able to automate. Sorry, you'll be able to automate certain task of network configuration. Let's say you want to roll out a new layer 3 VPN service, a new layer 2 VPN service. You want to do some sort of a device specific configuration. Then the next step is that you should be able to automate this process. Instead of, let's say, you want to create 100 layer 3 VPNs and do that configuration. So you should be able to do it with shorter time frame and with less involvement and with less overhead. So you need to have automation in the transport network. So to do that, there are a lot of aspects that you need to understand. One aspect is, in the modern, recently, telcos are looking at, also the vendors are bringing, this is mainly based on models. For an example, you can do network automation based on models. And one example is Yang and also YAML. And you can specify a network configuration of a network equipment using YAML or Yang or something like that. And then you should be able to do the network automation uh, based on that. And there are device specific Yang models and also service level Yang models defined by different industry organizations. And so this is how it would typically would work. This is sort of a slide that I have uh, put in to just to explain how this process would work. So usually you will have to work with different kind of model driven mechanisms to do the network configurations network wide. So if you want to do a rollout, let's say layer 3 VPN, so you can use service specific model to do the network configuration. And so if you take the orchestration as a whole, there are different community projects already out there. ONAP is one of them, and open source Mano. And then there are a lot of standards out there to specify how you would do the configuration, service level, network wide, and also on device level. So Metro Ethernet Forum has also defined certain specifications. IET Facton is a sort of a framework to follow if you want to do network orchestration and automation. And HCSM is sort of a high-level management framework to do zero-touch service management. So there are a lot of standards out there, and there are a lot of industry-defined Yang models or different models out there, and also device-specific models. Also, you can use if you want to do the automation. And in this space, there are a lot of vendors uh, having a lot of strong orchestration solutions that can do end-to-end service orchestration. And so those are the uh, main areas that you need to look at when you are doing network automation and orchestration in a telco network. Uh, so we have come to the end of this presentation. So if you have any questions and anything to clarify, then you can